This video lesson is going to help us capture some information about elements, chemical elements. First thing we need to make a note of is that this is not unit 0.1, this is unit 0.2. This corresponds to the Rosengarten text, pages 6 through 11. Elements. There are 118 elements in total, 91 of which are natural, and the rest are man-made. Man-made in a laboratory, in a synchrotron, where atoms are accelerated to very fast speeds, smashed together, and hopefully the particles stick together to make bigger atoms. But that's what we have so far, is 118 total, 91 of which naturally exist on the planet. Definition of elements: these are substances that cannot be broken down. They cannot be broken down by chemical means into simpler substances. We can, like we said before, we can smash atoms, and we recognize that we can break them down into their subatomic particles, but that is not a chemical reaction. So an element is a substance that cannot be chemically broken down into a simpler substance. So let's add that in there. It cannot be chemically broken down into a simpler substance. The elements are made up of particles that we call atoms. We represent them with symbols. The symbols have either 1 or 2 letters, and that has a very specific format. The first letter must be a capital letter, and the second letter, if there is one, needs to be lowercase. Atoms. Let's take a look at what we now consider to be the basic structure of an atom. This is not to scale. And I want you to draw a circle around these 4 circles. This circle that I have just drawn represents the nucleus. And in the nucleus are what are called nucleons. That's what these 2 represent. So nucleons are protons, which are positively charged, and neutrons, which are neutral charged. So nucleons are any particles that are found within the nucleus. Electrons are outside of the nucleus, and the whole thing with the electrons and the nucleus together is how we represent an atom. Of course, this one is not to scale, but it's just to so that you can see what is going on inside that nucleus. The definition of an atom: it is the smallest particle of an element. That still retains the properties of that element. They are very, very small. One can really not imagine fully how small they are. But if I were to take this seemingly random number, 6.02 times 10 to the 23, if I had 6.02 times 10 to the 23 atoms of hydrogen, if I had that many atoms of hydrogen, it would weigh a whopping 1 gram, which 1 gram is about the mass of a small paper clip. So what the implication here is that atoms are very, very small to fit that many in a sample size that's only 1 gram. All right, let's talk about the particles that make up these atoms. Right, we said there are something called nucleons. Right, nucleons are particles in the nucleus. And those particles are protons and neutrons. Okay, so we have protons. Taking a closer look at protons. Protons are symbolized with a P a lowercase p with a positive charge, because protons are positively charged. They have a mass of 1.67 times 10 to the negative 24 grams. That's a negative 24 grams. It's very, very small mass, and that's a very awkward, cumbersome number to work with. So for convenience sake, we say that that mass is equivalent to 1 atomic mass unit, which is abbreviated as AMU. Neutrons have the symbol N with a 0 because they are neutral charge. They have no charge. They have a mass of 1.67 times 10 to the negative 24th of a gram, which means that their mass is also considered to be 1 atomic mass unit. The number of protons in the nucleus is the atomic number of that element. And I'm going to put atomic number in quotes. The number of protons in a nucleus is considered to be the atomic number. That's an important piece which we will be practicing a few times. All right, so nucleons are protons and neutrons. Outside of the nucleus, we have what are called electrons. Right? Electrons have the symbol E minus because they are negatively charged. They have a mass of 9.11 times 10 to the negative 28th of a gram, which again, these individual masses are not numbers I'll expect you to know, but they are for reference. And really, you're going to need to know that protons and neutrons weigh the same at 1 atomic mass unit because their masses are the same. But this mass of an electron is significantly smaller than the mass of a proton or a neutron. So we say that it has a mass of 1 over 1,832 of an AMU. It's almost 2,000 times smaller than a proton or a neutron. The mass of an electron is so small compared to a proton or neutron that the mass of an electron does not really contribute to the overall mass of an atom. We say that the mass is fairly insignificant to the atom. The mass of an electron is just too small. Okay. Interestingly enough, the electron is responsible for the chemical reactivity of the atom or of the element. So if an element is reactive, it's because of its electrons. We should also say here that neutrons, the job of the neutrons is that they help bind the protons in the nucleus. Positive protons do not want to hang out near each other. They naturally repel each other. But the neutrons exist in the nucleus. It's something called the strong force. We're not going to really get into it at this point in the year, but that is simplistically what their role is. Okay, we've got this term of nuclear charge. If we think about what's in the nucleus, we have neutral neutrons and positively charged protons. So the only charged particle in a nucleus is the protons. So when we say nuclear charge, you're just counting the number of protons. Right? And so if we know that hydrogen, for example, hydrogen has 1 proton, so it has a nuclear charge of +1. +1 is the nuclear charge. If you had an atom that had 5 protons, the nuclear charge would be +5. The mass number of all of these subatomic particles, really only the protons and the neutrons contribute mass. So if we count up how many protons and neutrons there are in a nucleus, that count of nucleons will be the mass number. So the mass number is the number of nucleons in a nucleus, and you get it by adding the protons and the neutrons. It is always a whole number because you can only have whole protons and whole neutrons. Okay, let's go to the next page. Let's talk a little bit about isotopes and their symbols. Okay. The definition of isotopes is that they are atoms of the same element that have a different mass number. What this means is that they will have, the two atoms that you are looking at would have the same atomic number, which is the number of protons, but they will have different mass number because they will have a different number of neutrons, So, for example, we have 3 isotopes of hydrogen. This is hydrogen. We are just looking at the nucleus. We have removed the electrons. But this is hydrogen because there's 1 proton. If you have an atom with 1 proton, you have hydrogen. And so ordinary hydrogen is just composed of 1 proton, no neutrons. If you put a neutron into the nucleus of a hydrogen, so here's the 1 proton of this particular hydrogen atom, the total mass here would be 2. There's 2 total nucleons here. That hydrogen has a special name. It's called deuterium. If you add a second neutron to the nucleus, still 1 proton, so it's still hydrogen, this will have a mass number of 3. So 3 isotopes of hydrogen. They're all the same element because they all have the same number of protons, but each one has a different mass number. That's what makes them different from one another. Okay, we'll come back to that in a minute. Let's talk about how to write these isotopic symbols. How do you show these different elements, these different isotopes, using what's called the AZX format? I will refer to it as an isotopic symbol. Sometimes it's called nuclear notation. But the X is the element symbol. The Z, the number in the lower left corner, is the atomic number. Of course, the atomic number is the number of protons. And A is the mass number, which is the number of nucleons, right? Nucleons being protons plus neutrons. Okay, so knowing that format, let's try to capture these 3 isotopes of hydrogen in those symbols. So our first example, ordinary hydrogen, is sometimes written as hydrogen-1. This number right here, when you see a number after the name, this is showing you the mass number. And that means there's only 1 particle in the nucleus, and because it's hydrogen, that 1 particle has to be 1 proton. Okay, so this is, when we say hydrogen, this is the hydrogen we're talking about. Hydrogen has a symbol of capital H. Hydrogen has this 1 proton, so we're going to put that atomic number in the lower left corner. And the total number of nucleons, protons plus neutrons, is going to be 1, because there's only the 1 proton. Now deuterium is this isotope right here. It has 2 total nucleons, so the mass number is 2. So we would write the name of this as hydrogen-2. It's still hydrogen with that 1 proton, so we're going to put a 1 in the lower left corner. That 1 proton is what makes it hydrogen. 2 total nucleons has a mass number of 2. That's what goes up top. So let's take a look at the periodic table. Will have element symbols that looks like this. There's a little bit more information here. Of course, the Fe, that is the element symbol. And the whole number that is written here, this is the atomic number, which of course is the number of protons. That's what makes iron iron, is that it has 26 protons, right? That's the number of protons. This number up here is something called atomic mass, and it is not a mass number. It's related, and we'll talk about that in the next lesson, but for right now, atomic mass is not the mass number. This number down here, this 2-8-14-2, this is what is called the electron configuration. And if you add up those numbers, 2 plus 8 plus 14 plus 2, that is going to equal the number of protons. So if you add those numbers, it will equal the atomic number. The numbers in the upper right corner are what are called the oxidation numbers that are possible. We're not going to talk about those for a bit yet, but just to give you an idea that that's what those are called. Okay, a couple questions to draw out of this kind of information that can be gotten from the periodic table. First question, how many protons does an atom of iron have? Well, that's going to be your atomic number. Your atomic number is the number of protons at 26. If the question asks, what's the nuclear charge of an atom of iron? Nuclear charge is a charge, so you need to show positive, negative, right? And because there's 26 protons, the charge will be positive 26. How many atomic mass units, abbreviated as AMU, do the protons in an atom of iron weigh? So the number of protons is 26, each proton having the mass of 1 AMU, so this has a mass of 26 AMUs. Make sure you include the unit. That's an important answer to this question. How many electrons does iron have around its nucleus? 2 plus 8 plus 14 plus 2 is 26, right? And so this is assuming the atom is neutral, right? Because 26 protons is a positive 26, so you need 26 negative electrons in order to make it neutral. For right now, we will consider elements to be neutral. We'll talk about how to do this kind of accounting when the atom is not neutral, when you have something that are called ions. All right, that's it for this video lesson. There is a problem set to follow. Ask your teacher to give you that assignment, and otherwise, I will